So in the last class, I just want to go quickly on this generation of cosmic perturbation. So remember last day we covered almost finished section 3, which is inflation. It was an ultra short summary on the idea of inflation.
You want it? Is it yours?
Let's cover some. And remember that the main assumption is that there exists a scalar field, which in fact is quite homogeneous. So if you decompose it in a homogeneous part plus inhomogeneities, this inhomogeneity is always much smaller than the homogeneous part, and a potential satisfies an effective potential, and every universe is dominated by this potential energy. So the energy content of the universe is mostly that. And as I showed you last day, one can work out energy density and pressure. Energy density of a scalar field in Freeman-Robertson-Walker is always, remember, kinetic energy plus potential. Pressure is kinetic energy minus potential. I am talking about the homogeneous part of the scalar field. And therefore, if it is potential dominated, the equation of a state is just -1, and this is like a cosmological constant. So exactly equal 1 is a cosmological constant. So almost 1 is almost a cosmological constant. And you know that Freeman-Robertson-Walker, dominated by a cosmological constant, has A of t, which is exponential with time. So that means that here, that omega is almost 1, A of t is almost exponential, with h almost constant. And as I said, h squared is proportional to the potential. And this is what inflation is. So this is what I said last day, and the picture here is that you have a scalar field with a potential, and this potential, for instance, phi squared, and the scalar field is dominated by potential energy, so the potential is very high, and the velocity is very small. So phi dot is very small. And because it's very small, the field is rolling down very slowly. This is why we call it slow roll inflation, because the field is going down very slowly. And during inflation, we go down. And whenever it gets here and it oscillates, inflation is over, and we are in a different phase. Okay. So during inflation, slow roll down, h is almost constant. And I finished last day mentioning 2 parameters that we use to parameterize this slow roll evolution, which is epsilon and delta. Epsilon is has a minus sign by definition to make it positive, at least during inflation, and is how h changes compared to h in a Hubble time. The relative change of h in a Hubble time. So h prime over h squared. And during a slow roll inflation, h is almost constant, so this is much smaller than 1. When this gets closer to 1, inflation is over. And the delta parameter is the relative change of the second derivative of h as compared to the first derivative in a Hubble time, and I think for convenience there is a 2 there. And also during inflation, the slow roll inflation is characterized by delta much smaller than 1. These are the slow roll conditions. We are in a slow roll whenever these 2 parameters are small. So h is almost constant, and we have almost exponential expansion. So just, the intuitive picture that you have to get is that imagine that this is the universe, special section, and here imagine that I have, this is a very cheap picture. So it's just an artistic picture that you have, the scalar field, and the scalar field is, the universe is very homogeneous. But what happens here is that if you find a small region in the universe which is homogeneous enough, that region will inflate exponentially and will produce our entire universe, entire observable universe. So our observable universe will be just a small patch inside this inflationary spectrum. So maybe there is another region which also will inflate, but is causally out of contact with us. So we don't know this. We really don't know if this happened or not. The only thing that we believe is that some region in which we live in was inflating in the past. This is our assumption. Remember that the motivation for inflation was to solve this horizon problem that people call the fact that the CMB is made of very patches, a lot of patches which has been in the standard cosmology without inflation has been out of causal contact from each other. So you cannot explain why they have the same temperature. With inflation, you can. Also, why the universe looks like so flat, especially. Inflation also helps you to explain that. And normally, you need that the scale factor between the end of inflation and the onset of inflation, you need something like e to the 60 to solve those kinds of issues. So you need a period of exponential expansion in which any length in the universe gets rescaled by e to the 60. So the volume, any volume in the universe will grow during inflation by a factor e to the 3 times 60 because it's a volume, so you have 3 lengths. So this is something like e to the 180. In powers of 10 is something like 78. And with the current observations, if you compute how long inflation needs to produce that, you get something like 10 to the minus 36 seconds, 35. So I am telling you that people believe that the universe expanded 10 to the 78 in volume in 10 to the minus 36 seconds. So inflation is a bit crazy. Don't get convinced that this is just extremely nice because it has something which is extremely passive. So you cannot believe it for free. I really believe something similar to inflation happened. So I am not just discouraging you. I am just warning you that inflation is an assumption which is quite strong. In this extremely short time that even the strong interaction has interaction times much larger than that, in almost 10 orders of magnitude. Extremely short times, and it's shorter than everything that we have right now in our universe. The universe expanded in that way. That is quite possible. So this is an extra fast summary of inflation, but most of you know it, and also we don't have much time. So now let's go about the origin of cosmic inhomogeneity. Also, most of you know this, but anyway, I will explain it, although I will try to do it in a different way that you normally see it in papers or in books. So those of you who know it, at least will see something new or different. The motivation here is that we have what we call the standard model of cosmology, which is Friedman, Robertson, Walker model with Einstein equations. The universe is spatially flat. We now are dominated by the cosmological constant, which is very small. So the expansion now is also exponential, but the rate is extremely small. It's given by the actual cosmological constant. So we are living now in the second phase of inflation in the universe, but the rate of expansion is much lower. Before that, we were dominated by matter. Before that, we were dominated by radiation. And people work out this nucleosynthesis in the early universe. The early universe was hot, was dense, We had protons, neutrons, and photons interacting, light nuclei were forming, and we can compute the ratios of how much hydrogen versus helium versus lithium, beryllium, etc. And we measure, and we're in agreement. So that works extremely well. Also, that model predicts this hot Big Bang model that the early universe was extremely hot, and then predicts a CMB that people like Gamow and all these collaborators were able to predict the temperature. People went there and they saw it. A spectacular prediction. And another much more very nice prediction. So that model works very well. But also that model, if you take the CMB, if you take a picture of the CMB was formed in the really, really early universe compared to today. We see it's homogeneous with small temperature fluctuations here and there. Those temperature fluctuations in the CMB correspond to fluctuations in density in the early universe. And we know that density fluctuations will grow with time because of gravity. You will get clamping more and more. So people are able to take the CMB, put it in a computer, put Einstein equations, evolve it, and they see that the CMB inhomogeneities, they produce galaxy cluster, and the large scale structure.
How do they evolve such a long time?
These n-body simulations, which are extremely complicated. Of course, they have simplifications, but whatever they get at the end is quite similar. I mean, this is in complete agreement with large scale structure. And that is amazing. Take the CMB, where the density fluctuations were extremely small, the very early universe, and evolved numerically, and see that all the structure that we see around us is really coming from this tiny temperature.
Do they get the exact structure that we have, or like?
Because
we observe homogeneity in the
large scale structure is homogeneous, but at smaller scales you see something which is statistically in agreement. Of course, they cannot predict that there is a galaxy there, and a planet there, and a bird flying there.
Every pixel is like a galaxy cluster.
Right. So this large scale structure is really large, and every pixel is like a galaxy cluster or super cluster. But they get the large scale structures quite well, and that is very impressive. I think that is really a quite impressive work. But so we are very happy, but still we have to explain where are these primordial inhomogeneities coming from. These tiny density fluctuations in the very, very early universe, how they were created. Was the universe born with them? Were they there already in the Big Bang, or they have been generated dynamically by some process? The first reaction is thermal noise, maybe just thermal fluctuations, but what we see doesn't agree with thermal fluctuations, so it has to be something else. And this is where inflation. And it's quite surprising, because inflation was motivated for different means. It was motivated to explain the homogeneity, the flatness, and the absence of monopoles, and so the initial motivation had nothing to do with these inhomogeneities. But the same author who proposed inflation, Alan Guth, and other authors like Stephen Hawking, Starobinsky, Moganov, Guth, right? They at the same time was a lot of activity, and they realized that that now using quantum field theory on the inflationary spacetime, you can have this kind of particle creation or this quantum effect similar to the Hawking effect, and produce Hawking-like radiation, which is the origin of the cosmic inhomogeneities that we see today. So this is the idea that we are going to do now. Inflation. The proposal is that quantum field theoretical effects in an expanding universe, in an exponential expanding universe, have something, Hawking-like effects, that from vacuum you are able to produce a spectrum of density perturbations, and extremely tiny, super quantum, and that is the origin. So that happened even much before the CMB was formed, in the very, very early universe, just close to the Big Bang. And that evolved until forming the CMB inhomogeneities, and after the CMB, galaxies and galaxy clusters. And I always say that, to me, this is one of the most amazing ideas in physics, that, the entire large-scale structure, galaxy clusters, all this huge large-scale structure, is coming from vacuum fluctuations. Wow. Well, it's just amplification of vacuum fluctuations. We are nothing. The fact that the quantum vacuum is very different from the nothing. Quantum vacuum is full of, we know that what do you mean by quantum vacuum? There is no such thing as a vacuum. So the fact that the vacuum is something really rich and it's very different from the classical vacuum, which is the absence of stuff, that fact is what makes the whole universe to appear in this kind of theories. And now people believe in inflation because of that, because 3D produces something which is quite in agreement with what we see. So what I want to do here is to summarize that computation for you. And as you can imagine, this is one of the, together with the Hawking effect, and the Uber effect is one of the most important predictions of quantum field theory in core spacetimes. So this is the goal of this class today. Of course, we only have a class, so I cannot derive every single detail, but I think I have time to give you a good impression. And normally, this computation is done in momentum space, in Fourier space, that because you have seen most of you that many times, I will do it in position space, and then I will summarize also in momentum space. Both are equivalent, but I think the position space picture is, I would call it superior, because Fourier space is just a tool that we use. It's Fourier expansion. Fourier mode doesn't exist in nature. It's just a tool that we use. So the position space picture is if you want, more fundamental or more real than that. Sorry?
No, it's more mapping and.
Right, yeah. We measure in position space. Position space is many times called real space because we measure. Although there are some theories that claim that momentum space is more fundamental. Who knows? Okay. Okay, so we start with our system. And I also tell you that what I'm going to do is very similar to quantum fields in exact de Sitter space, because the inflation is almost the Poincare patch of de Sitter, because the evolution is almost exponential. This parameter is what deviates you from de Sitter. When this is 0 and this is 0, h is constant, we are in the Poincare patch of de Sitter. If this is small, we are in almost de Sitter. So quasi de Sitter space. This is what people call. The inflationary spacetime is quasi or almost the Poincare patch of the Sitter space. So our system is gravity plus a scalar field. As I said, in the assumptions of inflation in gravity, we have a Friedman-Robertson-Walker metric, Friedman-Lemaitre-Robertson-Walker metric, which is almost de Sitter, plus now I'm going to consider the small perturbations. Let me call it delta G mu nu. And for the scalar field, as I said before, we have the homogeneous part of the inflaton field plus inhomogeneities, whatever the deviation is. And the assumption is that this guy is much smaller than this guy. So this is really perturbations. As I discussed in the previous section, these two guys, they together, Einstein equations, they produce inflation. So we already took care of the physics of the homogeneous part. Now we have perturbations, this guy, and this is what I want to study. How many degrees of freedom we have? We have 3 degrees of freedom, 2 from gravity, 1 from a scalar field. So we have really 3 physical degrees of freedom. Delta G mu nu, it has 10 components. It's a symmetric matrix 4x4, but only 2 degrees of freedom are physical. The other ones is what we call gauge or coordinate dependent fields. And normally in cosmology, what you do is you take all these functions and you extract from that what are the gauge invariant degrees of freedom. And there is a systematic way of doing it. We did it in the cosmology course. And wherever you get the gauge invariant degrees of freedom is 1 scalar that I'm going to call R and 2 tensor. So it's 3 degrees of freedom. This guy is what we call comoving curvature perturbations. So you can understand this guy as the fluctuations in the scalar curvature of the universe, or if you want, the gravitational potential in the non-relativistic limit, this guy goes to 5, I think it's 5/3 or 3/5, I never remember, the Newtonian gravitational potential. So you can think about that guy in that way, the gravitational potential. The other two degrees of freedom are the two polarizations of a gravity wave. If we don't have matter, gravity is just gravity waves, only radiative degrees of freedom. If we have a scalar field, then we also excite a scalar one. I am not deriving how to extract from the metric and the scalar field these gauge invariant variables, but there is these are the gauge or coordinate independent perturbations. Where gauge in GR, the gauge group of GR is just the change of coordinates, the group of diffeomorphisms. This is why people call that gauge invariant. So the strategy here that we are going to follow is to treat these three gentlemen, the scalar and tensor perturbations, plus and cross, as fields themselves propagating in the inflationary spacetime. So realize that these are just perturbative degrees of freedom of our initial degrees of freedom, but we have to split them in background, metric, and scalar field. They produce inflation, and the perturbations are just, we can see them as fields living on that spacetime. So forget about that they are coming really from the metric, and close our eyes and say they are just fields that propagate on this inflationary spacetime. This can be done because they are perturbations, because we work in perturbation theory. So these guys propagate on the top of that, and this guy doesn't realize, because this guy is so small that the propagation of this field on that doesn't modify this gentleman. So this works because we are in perturbation theory. And we are going to quantize these gentlemen. So if you want, we are going to do quantum gravity, because we are quantizing gravitational degrees of freedom. Although only perturbative quantum gravity, which is the easy part, the easy part. But we are putting h bar on gravitational degrees of freedom, so strictly speaking, we are doing quantum gravity.
There are people who say this is quantum gravity.
Some people say this is quantum gravity, and they are right. It is only perturbative quantum gravity.
And another thing is that this is the only few places where you have gravity and you can observe gravity and quantum mechanics together.
Quantize gravitational degrees of freedom. That is completely true.
I mean, where you can observe also.
Right, and observe, of course. So many people believe that the CMB observation, if the CMB inhomogeneities are really coming from inflation, then you are observing quantum field theory in corpus mechanics. But we have to see tensor modes to be completely convinced that what we see is coming from inflation and not something else. But if we measure tensor modes, first observation of the quantization of gravitational degrees of freedom, although at the perturbative level, and also the first predictions of quantum field theory in quantum designs, measure, observing. The difficult thing is to be able to show that is coming from that effect and not from something else. This is what we have to fight, and this is why tensor modes are so important. Okay, so we are going to do quantum field theory of curvature perturbations, of scalar curvature and tensor curvature. These are normally called tensor modes, and this is scalar, in an inflationary spacetime. And you know how to do quantum field theory, so just take that and do it. So I'm going to start and essentially show you the computation for scalar perturbations, which are maybe more difficult than tensors. That sounds weird. Normally scalars are easier than tensors, but not in this case. The only point is that tensor perturbations, each of them, they satisfy exactly the same equation as a scalar field. So tensor perturbations are like the two components are like two scalar fields. So that is simple. This guy satisfies an equation which is not exactly the same as a scalar field, although it's very similar, and it has not a big difficulty. Maybe the biggest difficulty identify that this is a gauge invariant degree of freedom. I skip that. Okay, so scalar perturbations, and I'm going to do the quantization. As you know very well, the first thing I have to do is to write the equation of motion, the classical equation of motion. If you do perturbation theory in GR, you will find that this guy satisfies this equation of motion. I am working in the conformal time, so this Z only depends on conformal time. The field depends on everything, on space and time. Prime, as usual, is derivative with respect to conformal time. This is the equation that this guy has. I have to tell you what this Z is. Remember that when A is here, if I put A rather than Z, I have a Klein-Gordon field. This was the same equation as a Klein-Gordon field. But now I don't have A, I have Z. And Z is really proportional to A. But it has another factor in front of it, which is the time derivative of the background infraton field over the Hubble ray. And dot, remember, dot is derivative cosmic time, prime derivative conformal time. So it's almost the equation of a scalar field, except for this guy here.
And the dot is with proper time, or
Dot is proper time.
oh,
Now you are experts on quantum field theory. I ask you know how to quantize that, and you would say yes, and then I say how, because this is not a Klein-Gordon field, and you have been learning so far how to quantize a Klein-Gordon field.
Doesn't matter.
But what is the scalar product? This is not the Klein-Gordon equation. What is the inner product? So far we use the Klein-Gordon inner product, but this is not a Klein-Gordon field.
The Klein-Gordon product has the Klein-Gordon current in it. Can we define another sort of current relevant to this one?
That's the question. Can we? The answer is yes. Of course. There are different ways of doing it. If you ask me, the more formal way is to realize that this current is just the symplectic product, and I can compute what is the conjugate momentum of this one, of R, and just write the symplectic product, and I will obtain it. There is a cheaper way, which is faster, is to realize that, the important thing here in quantum in corner spacetime is not Einstein equations. We don't use Einstein equations for anything. The metric is given for us, and it's just fixed, and we propagate a field on the top of it. So we don't care where the metric is coming from. The only thing we need is a metric. We don't care if it satisfies Einstein equations or not. But this is the equation of a Klein-Gordon field satisfying on this metric. If you replace A by Z, and you write the Klein-Gordon equation for R, you will get this equation. So whenever you see A in the Klein-Gordon solutions, in the Klein-Gordon theory, you put Z and you will have a correct inner product. So we can do the same, just changing Z by A. So therefore, we can follow the standard strategy. We can follow standard strategy, which is find the space of complex solutions. They choose a positive and negative frequency decomposition. From that, write the one particle Hilbert space, the focus space, the vacuum, etc., and do physics with it. So this is what we are going to do. So the first thing I want to do is to exactly do this. Find the space of solutions and choose a positive frequency decomposition. As I did in previous section, in the reciter one, or even in the first of the chapter, very convenient to use Fourier expansion. So write this field as the Fourier transform of something else. and then the equation of motion for each Fourier mode is the one that we wrote for the scalar field, changing A by Z. It's like a massless scalar field with changing.
Yeah, you have a double prime in the first equation, top.
What's that? Maybe one prime. I need to write explicitly what this Z prime over C is. That can be done just using the Friedman equations for A and phi naught dot. I'm not going to do it because it's boring and it's nothing new there. Just telling to you that the result is 1 plus 2 epsilon plus delta plus order epsilon and delta square. Remember, epsilon and delta are the slow roll parameters, and they are small during inflation. So from now on, I'm going to keep only first order in a slow roll. This is what we call slow roll approximation. I'm going to neglect whatever is second or higher order in a slow roll, and that is an excellent approximation during inflation. So if I forget higher order terms, also, if you compute the time derivatives of the slow roll parameters, they depend on time. You can compute the time derivatives. They are also of order epsilon and delta square. So that means that in the slow roll approximation, you can treat them as constant. That simplifies a lot. So therefore, epsilon delta are constant in the slow roll approximation. Just tell you that this is a differential equation for C that we can solve. Remember, just the important thing that you need to know is that in a slow roll inflation, the relation between A and the conformal time is this. Remember, in the zeta is just this part. In a slow roll inflation, one has 1 minus epsilon. That can be seen easily.
You're saying that's like an order parameter of order e delta squared, or is that function?
This is order square in those parameters. If you solve this differential equation, you will get, and this will be useful later, that Z is the initial value of Z, eta over eta naught, where eta naught is an arbitrary initial time, minus 1 plus 2 epsilon plus delta. And this is quite easy to obtain. And of course, all the time at first order in the row. I will not keep writing second order, so from now on, everything is at first order in a row. Keep this expression in mind because it's very useful. Really useful in a second. So now I'll bring Z prime over C to the Kling-Gordon equation. I have minus 2, 1 plus 2 epsilon plus delta divided by eta, first derivative plus k squared eta equals 0. This is the equation that this guy satisfies. In general, if epsilon and delta are functions of eta, are complicated functions of eta, this is difficult to solve. But if epsilon and delta are constants, which is what we are same in the slower approximation, they become as constant. Then there are analytical solutions. The most generic solution, it happens that this is a Bessel equation, as the one that we found in the zeta space. So the solutions are very similar to the ones that we found in the zeta space, except that now we have z rather than k. We have the Hankel functions. And the only another difference is that the index of the Hankel function now is at first order in roll is 3 over 9 plus 2 epsilon plus delta. Remember in the center it was like 9 over 4 plus mu squared plus 12, this guy h squared over 8. Epsilon and eta, this is replaced by epsilon and eta. And if you expand the root square, the 9 over 4 becomes 3 over 2. And whatever appears here becomes this plus higher order in a slow roll that we are neglecting. So this 3 over 2 comes from a root square of 9 over 4 that we had in exact center. Okay, we have the most generic solution to the temporal part of the solutions. The x part is the exponential. So if you take this for any values of e and f, you get the space of solutions. So this provides the space of complex solutions. It's made of these guys multiplied by e to the I k x. So guys of this type belong to that. These are, of course, any linear combination of guys of this type is a solution. Next step, make a choice of positive frequency basis. Decompose this guy to positive and negative frequency. This is the typical problem in coordinate spacetimes. In general, we don't have a preferred decomposition. But here, remember in the sitter, we were using the 7 symmetry group of the Poincare patch to select E equal 1 and F equal 0. Now we don't have exact de Sitter symmetry because we are not in exact de Sitter. So we don't have, strictly mathematically speaking, we don't have those isometries. But we are very close to the Sitter. We are, almost de Sitter because epsilon is close to 0 and delta is 0. So it's natural to choose something which mimics the de Sitter mode, which is just choose E equal 1 and this equal 0. So a natural choice, and I say a natural because mathematically we don't have symmetries. And we have homogeneity and isotropy that we don't have, strictly speaking, this additional Killing vector field. A natural choice is what people call the Banks-Davis modes. Banks-Davis, using the analogy with the Sitter space, in the Sitter we call them Banks-Davis, so we call them here also Banks-Davis. And this is the natural extension of the Banks-Davis modes to almost the Sitter slow roll inflationary spacetime. Mathematically, you could choose something else, and I couldn't complain because, strictly speaking, I don't have a symmetry. But I agree that this is the most natural extension of the Banks-Davis vacuum to almost to quasi de Sitter space. So these modes are normalized. They are, therefore, our basis of positive frequency modes is made of these Banks-Davis solutions e to the kx for all k. They are normalized to 2 pi cubed and the delta function, the delta of 0. The same as the Banks-Davis nodes. So this is the Banks. So with this, I define a one-particle Hilbert space. This, as usual, provides a decomposition of the complex space of solutions. I'm going to call the Banks-Davis decomposition. And the Banks-Davis one-particle Hilbert space, the Banks-Davis focus space, and the Banks-Davis vacuum. Now don't forget that this Banks-Davis name is an extension of what we have in exact ether. We are not in exact ether, but it's the name that people use, and it's also I find it a reasonable name. If I have to choose a vacuum, I will also choose this vacuum, and I will also call it Banks-Davis vacuum. Now, therefore, we have a representation of the field operator. We have a full quantum theory, so a Fock representation, which is the Banks-Davis modes e to the I kx A of k, let me call it A Banks-Davis, plus the mission conjugated, and I am ready to do physics with it. In particular, I can compute the 2-point function, which is, as I emphasized many times, is the key object in a free theory. The 2-point function is very similar to the one in exact ether. The only thing is that now we have z rather than a, and we have the index of the Hankel function is slightly different. Again, let me just write the 2-point function for equal times, because it's what I will need in my computation for inflation. For different times, it's almost the same. H bar that I forgot the other day to write H bar. Two gamma functions. And now the hypergeometric function. You can see that this is, if you put z, if you replace it by a, has exactly the same form as in exact ether. But here new means something different. Delta x squared divided by 4 eta squared. This is the 2-point function. We have an analytical solution, very nice. Remember, we are in the slow robot optimization. So this is why we find analytical solutions. And given the 2-point function, I can compute whatever you need. If I cannot, Rajesh can.
All right. I'll take that.
It is interesting to explore the form of the 2-point function in two limits, the ones that I mentioned on Tuesday. First limit. When the 2 points, the physical distance between the 2 points is much smaller than the curvature radius, which is 1/8. You can put that in Mathematica, expand, the only thing you have to do is to expand this Hankel function, this hypergeometric function in that limit. Remember that eta is 1/a, so you have this combination squared in the numerator, so you can just put in Mathematica and expand, and you will see that the 2-point function, I mean, physically this means physical distances much smaller than curvature radius. So as I said the other day, you expect that the curvature is completely unimportant in that limit. So you expect to recover Minkowski spacetime physics. And that is in fact the case. This should be a check, but because today is the last day, you can check it if you want. So if you do it, you will obtain h bar over z squared 1 over delta x squared, which, remembering the definition of z, this is just h over 5 dot not squared 1 over a squared times. This is just the Minkowski two-point function for a scalar field. Now, remember that R is a scalar field except for the difference between Z and A, which is precisely this factor. So this factor appears because R is not a scalar field. It's a scalar field up to this factor. So we recover what we expected. Minkowski-like physics on that regime. The other limit is what is even more interesting for physics. The other limit is when physical distances are much larger than the radius of curvature. So in that case, it's also a good exercise to expand in Mathematica the hybrid geometric function. And this is what you obtain. Minus h bar 3 halves minus mu 3 halves plus mu. I have here in my notes a mu, but it's probably because I forgot 3 halves. Probably. And now you have this minus theta 2 mu minus 3 over 2. You like it?
No, it's pretty.
So let's see a couple of interesting features. The time dependence. So the time dependence appears here, and in z, remember z is a function of eta and eta. So the time dependence is eta to the minus 2 mu minus 3 halves divided by z squared eta squared. All the rest is time independent. Now is where I'm going to use how z evolves with time, where I wrote there. So let me flag that there. Remember that z, the function of eta, is a constant. Remember, eta naught is just an arbitrary initial time. And note that the exponent there is just minus mu minus 1 half. Because mu is 3 halves plus 2 epsilon plus delta. So if I plug that there in the numerator, I have mu minus 3 halves. In the denominator, I have. Let me forget about the constant. Doesn't matter here. It's eta, square of that, so minus 2 mu minus 1 half. Eta square. So this square is going to give me. So here I have minus 2 nu, which cancels with this 2 nu. And here I have plus 3, and in the denominator I have plus 2, plus 1, plus 2, 1.
What question is this when ax squared is much greater than 1 over h, or should it just be ax? Like
This is a square here. Sorry. Thank you. So, important. The 2-point function becomes time independent. During inflation, if you take 2 points and you look at the correlations between these 2 points, when the 2 points are separated a distance much larger than the curvature radius, the 2-point function doesn't, and you put time on, the 2-point function doesn't move in time. Constant. Also from here, something very important. We can see what is the x-dependent. The x-dependence, so the 2-point function depends on the distance between the 2 points. It's homogeneous and isotropic, only depends on the distance between them and not on the direction. And it goes like 2 eta minus 3 halves. So let me define here what we call the spectral index.
So is that first point the same as saying that the modes are frozen when they're outside the horizon?
Exactly. This is the space-time, the position space version of that.
Okay.
But it's exactly the same. Let me define what we call by a spectral index, 1 minus ns. This is the definition of ns. Ns, which is called the scalar spectral index. Scalar spectral index is defined as this, as 2 mu minus, I think it's minus, I don't know if I lost that.
That's good. 2 nu minus 3.
This is what it is.
Yeah, that sounds good. That
Which is what?
yeah.
So this is just delta x 1 minus ns. And if you remember what mu is,
So that's in the parentheses nu minus 3 by 2.
that's in the sorry.
So 2
Let's
nu
just-
minus 3 by 2.
That
in
should
the
be in
first
bracket.
Twice
Yeah.
no minus.
I see. Which is what I have. Right?
Yeah.
Right. So remember, mu is 3 minus 2, 3 over 2 plus 2 epsilon plus delta. So the 3 over 2 cancels, and what I have here is 4 epsilon plus 2 delta. And this is much smaller than 1 because we are in a slow roll. So this is. So what we see is that the 2-point function is almost independent of x when we go to the limit of super Hubble scales. Only depends, but it's not completely independent. Depends on x, but in an exponent which is almost 0. This is what we call almost a scale invariant. So conclusion, the 2-point function is almost, in that limit, becomes almost scale invariant. And when we take, because this is positive, so when we take distances larger and larger, the 2-point function grows. So it is larger for infrared distances because the exponent is positive. So it grows very slowly, but it grows. So it's what we call red tilde. Red tilde means that it grows for infrared. So the predictions of inflation, so far I have done, I am just doing mathematics. Now I will do physics. But the mathematics I am doing is that in the inflationary space-time, if scalar perturbations are in the Weinstein vacuum, it happens that the 2-point function mimics the Minkowski 2-point function at very short distances compared to the curvature, and when the 2 points are out of the curvature radius, the 2-point function becomes time independent and almost independent of x. So if this is the curvature scale, then the 2-point function almost doesn't change if I take each point or each point to each point. the correlation between them are exactly the same, except for this small factor, which is red tilde. Now we can do physics with it. Sorry, no. One more thing. The last thing I want to do is to, this guy is time independent in those regimes. So I can put eta wherever I want. That number will not change because I just showed to you that all eta cancel. So I can put the value of eta that I like. I can put 27, I can put 57, I can put wherever I want. This number is going to be always the same because all the eta cancel. So I'm going to put a number there which is convenient to write this in a nice way. So substitute t, eta, I'm going to use what people call eta sub absolute value of delta x, which is the time at which this is equal to h. So what I'm telling you is that, we are in the inflationary space-time. H is almost constant. 1 over h, or 1 over h. So 1 over h is this line, is almost constant during inflation. Depends on time, but very slowly. Now I take 2 points separated by coordinate delta x. The physical distance between these 2 points is that multiplied by a. So the physical distance between 2 points is growing with time. There is a time at which the physical distance is equal to the 1 over h. This time, if time is growing in this direction, this time is what I am defining as. So is the Hubble exit time for that distance. This is what we call the Hubble exit time for this separation. If I substitute that time in that expression, I get a very compact expression for the tubing function. And now I will mention a subtlety that appears here, and it's a confusion even in momentless space. So the tubing functions evaluated at points which are separated a distance much larger than the Hubble radius is given by ns minus 2. So it's just an exercise, to manipulate this and put eta where I'm using. And in 2 lines, you get this expression. 2 times the Planck mass square epsilon h evaluated at eta of delta x over 2 pi square.
So isn't it slightly inconsistent? Because in obtaining this time independence, we assume that a delta x is very, very larger than 1 over h. But then we are putting eta with
very
that
good.
condition.
This is precisely the subtlety I want to discuss. This is why I will discuss that subtlety now. The same happens with mode functions.
Yeah.
They get frozen much after, but we evaluate them at the Hubble crossing time.
Yeah.
But we are not evaluating. We are substituting.
Yeah.
This is not the value of the 2-point function evaluated at the time. No. This is the value of the 2-point function when the 2 points are much out. When we substitute for this eta that value. But the 2 things are different.
But this is independent of
Right.
eta anyway.
In that limit, that is independent of eta. So you can put the value of eta that you want, and we put that value. But that is different from taking the whole 2-point function and evaluating it at the time. The 2 things are different. And for most, there is a factor 2 of difference, which is is a common mistake in many papers, in particular on the original papers. Now people know that.
What factor?
On the origin, a factor, for the modes, these guys, as I will write in a second, they also become constant when the mode is outside the Hubble radius. Then you can take that constant, and wherever it is a eta, eta is really not there, so you can put eta sub k, and you get a number. But the number that you get, if instead doing that, you put here eta k, they should differ by a factor 2 or the square root 2. So it's not the same taking the whole tubing function and evaluating that taking the asymptotic form of the tubing function and substituting. You are not evaluated anymore. That is already evaluated. Substituting a convenient value of eta. I could choose eta equal minus 100, or it doesn't depend on eta. I can just put a convenient value, so I have here convenient functions.
Yeah.
So can you evaluate these 2-point functions either numerically or computationally at values in between?
Yes, of course.
Okay.
You can do it, and you can see how it becomes constant, how it becomes almost delta x independent. So I mean, this is the way that we do it in computer. This is nice because it's analytical, but you are doing an approximation which is neglecting epsilon square terms. You can do it exactly numerically, and you can check that this approximation is simply good, and you can play as much as you want. I have to define for you this MPL. This MPL is what cosmologists call reduced Planck mass. The Planck mass normally is a G here in units in which h bar of I forgot an h. I forgot to check the h bar. There is a h bar for sure here. Well, it is possible that there is another h bar somewhere there, and I don't remember it.
It's there. There is an h bar there.
Right, but now when I write the Planck mass here, it's possible that I have to introduce another h bar, and I don't remember where it is. H pi here. So this is what people call the reduced Planck mass. And this h pi is convenient because it would appear in Einstein equation. But it's a bit of confusing because in Einstein equation is purely classical. There is no h, and people call it the Planck mass. And the Planck mass is really quantum. So at this point, just understand this as this factor. And I cannot tell you exactly how many h bars are there because I don't remember. Okay, so let me now do physics with it. So far, just a mathematical statement about the behavior of the 2-point function of a scalar curvature perturbation in a slow roll inflation. Now, the physical picture. So now, time will grow vertically. Imagine that this is today. And we start here at the onset of inflation. Eta onset of inflation. Let me draw here the Hubble radius. It's 1 over h. We call the Hubble radius. It's also the curvature radius. It's the characteristic scale of the curvature of the spacetime, which is constant. In inflation, we know that the curvature radius is constant because h is constant. Remember, the zeta is the space with constant curvature. So this is the end of inflation. After inflation, we have a gap here of the stuff that people doesn't understand very well. It's what we call reheating. Remember reheating? I don't know if I emphasize it before enough. Remember, in inflation, the scalar field starts at some position in the potential. This is the homogeneous part of the scalar field. So at some time here, goes down, inflation happens. All this is slow roll inflation. And at the end, this guy oscillates. Inflation ends, and this is what we call reheating, because in this oscillation, it is supposed that the scalar field is going to radiate all its energy in photons, electrons, positrons, and protons, and fundamental particles. So it's at the end of inflation when the universe becomes really hot, and this is why we call it heating. But we have a re inside for historical reasons. Now it should be just heating, but for historical reasons we call it reheating. And this is what Lemaitre and all the people dream about the hot Big Bang model. The hot Big Bang, when the universe becomes hot, is this point. What he called the primeval atom and all that. That happens here. So this is where the hot Big Bang. Big Bang, not in the sense of singularity, but in the sense of the universe becomes full of particles, very dense and very hot.
So before that, there is no sense in which we can ask about the temperature of the universe.
No, because it's just a scalar.
Because,
Because
there's no thermal property.
okay, so what is the picture? So, and important. Now I'm going to draw the radius. Sorry. After reheating, we have radiation domination for a while. Radiation domination, and then matter domination. And now we are here, dominated by cosmic level constant. You can follow this guy, and this guy does something. I mean, here it does something weird, and that we don't understand very well. And then it grows linearly with time, with cosmic time. So I should write cosmic time. And here also linearly with a different slope. This is where the CMB is formed. This is what we call recombination, and it's when the CMB is formed. And we are here observing the photons that arrive to us from the CMB, which is something like a sphere. This is the photons. This is the CMB. And we can also follow what is our observable universe. Imagine now. That this is our observable universe. This is observable universe. The statement is that the observable universe in the every universe was something like that. Inflationary patch is much bigger, and this is the part that grows exponentially, and then evolves something like this. So this is the evolution in green of our observable universe. If you get our Hubble radius today, you evolve it backward in time, this is what happens. So then, the way that we put physics on this is the following. First, we need to make we want to study scalar perturbations. First, we need to make an assumption about in which state the scalar perturbations were at the onset of inflation. And the assumption is the following, is that in our observable patch, this scalar field was in the vacuum. That is quite reasonable because we only need to make assumptions about a very small patch, which is extremely small compared to the whole to the curvature radius. In inflation, we don't need to make assumption about how the field is at this point or at these separations, because that scales are out of reach in our sky today. So we only need to make assumptions about this small patch, and it's so small compared to the curvature that it is reasonable to assume that the perturbations were just in the vacuum state there. You can put a question mark, why the vacuum? Much of my work in the past has been devoted to that. But, it's quite reasonable. If you have to choose a state for perturbations, at least in that small region, I think it's quite reasonable to choose the vacuum. So then what happens here is that, points here, initially the vacuum is like the Minkowski vacuum, as I showed. So here, the Weisser is vacuum. Therefore, our computation tells us that at the onset of inflation, the 2-point function is like Minkowski. But then inflation appears. Take these 2 points and bring them outside the Hubble radius. In this process, we have the transition from the Minkowski form to this form, to the final form. So in this transition, curvature will take Minkowski vacuum fluctuations and will transform them in this kind of vacuum fluctuation, this kind of correlations. In such a way that once the 2 points get outside the Hubble radius, the 2-point function doesn't evolve anymore. It's constant with time, and becomes x independent. So the dependence in x is going to be quite weak. So it doesn't matter if I started from these 2 points, or these 2 points, or these 2 points. The 2-point function at the end is going to be very similar, except for that small red tilt that we have over there. We don't understand what is the physics here. But that doesn't matter, because the 2-point function is constant in time. Doesn't care about what happens there. So this is what is really nice from inflation. That takes microscopic physics, makes like a magnifying glass, brings them to cosmological scales, and frees them. Physics that we don't understand happens, our 2-point function doesn't care about that. Our 2-point function will only start evolving again when these 2 points become again smaller than the curvature radius. So during the whole process, from here to here, we have frozen 2-point function.
So is that because they're out of causal contact? Or?
You can think that in that way.
Because
I mean, this is the
otherwise it seems like, we don't know what's happening. They could decay, they could interact, but they can't interact if they're out of causal contact, right?
But people use that sentence, but I never know what it means, because that's 2 points, or are in concept of what?
Well, that's true. It's space-like, right? So
2 points at the same time are always space-like separated. So,
yeah.
If you try to make precise sense, you never know how to make precise sense of that statement. But the intuition is that that constant physics happens inside the Hubble radius and wherever it's outside. For me, this computation is what gives me this.
Well, but how does that stand up once there's interactions?
Sorry?
How does that stand up once there's interactions?
If there are interactions, this also should work.
Okay.
And in fact, I only showed that this is frozen for inflation, and I am telling to you that also happens after inflation. And there are proofs of that this quantity becomes constant over there. So, important points. Point 1, we assume vacuum fluctuations. I lost my. Point 1, we assume vacuum fluctuations. Point 2, at the end of inflation, fluctuations have grown and frozen. This implies that at the end of inflation we have a spectrum of curvature perturbations. Curvature. So this is telling to us that at the end of inflation, our curvature perturbations is non-trivial. It has this 2-point function. So you can imagine that we have here a spectrum of quantum curvature perturbations described completely by this 2-point function. Then reheating happens. Electrons, photons appear in the universe. It is matter. Wherever there is excess of curvature, they will go there. So these curvature perturbations, together with reheating, will become density perturbations. So again, we have curvature perturbations described by this. When reheating appears, photons, electrons will try to follow just by gravity, where curvature is larger. They will try to accumulate where we have more curvature. So this spectrum becomes density perturbations. That spectrum becomes frozen until they re-enter. So at point 3, perturbations or fluctuations re-enter the Hubble radius. So they start evolving again. And that is okay, because we know what is the physics of the universe at that time. And point 4, which is where the CMB is formed. Point 4, photons in the CMB acquire those inhomogeneities, we have a spectrum of density perturbations there, and of course photons, we will have more photons whenever the, where are you talking about? Any
Photons.
we have a spectrum of density perturbations. There will be more photons whenever there is more gravity, or the temperature of photons will be higher, or if you want, they will have to escape a valley in gravity, so they will be more rev shifted when they try to escape a valley. Imagine that we have a valley in the curvature or a hill. Photons here will be more rev shifted, and photons here will be more blue shifted. So, in summary, this two-point function that we are creating in inflation will be reflected in the temperature distribution of photons in our CMB. So these small curvature perturbations are the source, are the seeds of the inhomogeneities that we see in the CMB, and therefore they are the origin of the large scale structure. So that is the short picture. But we have a prediction. We have a prediction for the statistics of the CMB. Somebody's telling us that this is what you should see in the CMB. So if you believe me, go to the CMB. Start measuring temperature. 2 points. Take the 2 point. Check. Go to the CMB. Compute the temperature in one direction. Measure the temperature in one direction. Measure the temperature in a different direction. N prime. Take the average, the statistics of that, and compare it with it. Does it agree? The answer is yes. What we see here in the sky is precisely an almost scale invariant. And the almost is crucial. Scale invariant spectrum of temperature. So this theory, at least quantitatively and at a certain degree, of course one has some freedoms, but it captures very well the details of the statistics of the temperature distribution. Of course, we cannot predict if there is an excess or a deficit of temperature in that direction. The best we can predict is the average, average in the CMB. So the statistics of the CMB, how they are distributed statistically, and they agree with what we compute.
How do you constrain both delta and phi, or delta and epsilon? I mean,
Delta and epsilon are just your free parameters. That depends on your potential. You give me a potential for the scalar field, and you can compute epsilon and delta. So they are model dependent, if you want.
Okay, so they vary. They vary differently with the spectrum with the exact numerical model.
Right, exactly.
And so they're two free parameters in the spectrum,
right.
And they're independent.
Right, but they are very small. This is what we say. They have to be compatible with the whole model. They have to be order 1/100. And this is quite generic from inflation. The value is model dependent. What is generic is this small value, and this is what we see. This almost scale invariant spectrum that we see has the slope given by 1/100, which is exactly the same slope as we are predicting here. By the way, here the x dependence is here. The x dependence I was mentioning before is here. So this guy depends on the separation very slightly, and that dependence is here. So, to tell me what exactly epsilon and delta is, I need a model of inflation. I need a concrete potential. Which potential your scalar field takes. And of course, there are infinitely many potentials. This zoo of inflationary models. Some people say that with inflation you can predict everything. And they are partially right.
Yeah, because we can take any potential.
Right. But this prediction, this almost scale invariant, is quite generic from all models. It really captures at least the simplest models of inflation, and this is what we see. Is this enough to say that inflation happened? No, because as you say, inflation has a lot of freedom. So how we can test if inflation happens? Computing more predictions. What is the other prediction? Tensor nodes, this gravity wave. If you do the same computation, you will also produce a very similar spectrum. The only thing is that this number change, a spectrum of gravitational waves. And therefore, the efforts now is in observing if that spectrum is also in the sky or not.
But
So-
that has more parameters, right?
I mean, the model is the same. With the same model, you are predicting both the scalar spectrum, which produces temperature anisotropies, and a spectrum of gravity waves.
Right, but it has like a couple additional parameters, right? Like a tensor parameter and a.
I mean, this E and B polarization, or
Right, but I don't remember, is there another parameter beyond epsilon and delta? Do you need?
No.
do you mean the tensor to scalar ratio? This R? Or
Yeah, exactly, something like that, yeah.
This is just the ratio of tensor versus the amplitude of tensor perturbations compared to scalar. So this is a prediction that the model is making. If I repeat the computation and I take the ratio between the amplitude of scalar and tensors, this R is that. And you give me a model. I mean, epsilon inflation predicts this to be 16 epsilon.
And it's
And epsilon is
independent
1 per
of what potential you choose.
Right.
It's independent of. the
No,
potential.
it depends. Epsilon depends on the potential. But it's 1/100 is the order of magnitude. Or if you see R, which is 25, inflation is wrong because you need epsilon order 1, and that is incompatible with the model. If you see this to be of the order of 0.16, then inflation is producing that with some potential that we don't know. So the statement is that inflation also makes a prediction for tensor perturbations, and this is what we are trying to measure. And BICEP 2 had a claim for observing those, but it didn't happen. So now there are a lot of other experiments. We are trying to see those primordial radiation waves, because if we see that, then we have two different predictions for inflation being checked, and we can check if everything matches. Because remember, there are two different predictions, the scalar and tensors, and there are relations between them because the same parameters appear in both. So we can check if these two independent observables have the relation between them that inflation is predicted.
So
I forgot to say that realize that this diverges in the zeta limit. But that is normal because there is no massless scalar field in the zeta space. So if you put epsilon equals 0, you are reducing to a massless field in the zeta, and you should recover the infrared divergence that was mentioned before. So that is not a problem in inflation. That is okay. Sorry.
so the ratio between these two depends on what potential you choose.
Right.
So then you can come up with any ratio that matches with the.
Right, that is true. That is the complaint. But not with any, because epsilon, the ratio is 16 epsilon. And epsilon, you can compute this, the first derivative of the potential over the potential square with some 1 over Planck mass or whatever. So it depends on the potential. And you cannot, inflate, if you measure this equal 1, that is incompatible with inflation.
No, but you're saying this R equal to 16E can be a different value of R if we take a different potential.
Exactly. But because epsilon depends on the potential. But
Okay.
if you measure, imagine that you come and you say,
So
R
for
is
any
25.
potential, it's going to be 16E
Exactly.
with the potential dependence inside E.
Exactly.
Okay.
And E has to be order 1 over 100. Can be 1 over 500, can be 1 over 1000, can be 1 over 10,000, but cannot be 1. If you measure 25 in R, inflation is ruled out. I mean, inflation cannot generate that. Somebody will come with a model with 25 fields coupled in a different way. But I will not be happy with that. As usual, you have a model which you put some assumptions which are strong. But if you get much more than what you put in, then you are happy with the model. Of course, if to see the sky, to reproduce the CMB, you need extremely complicated model of inflation, not with one field, but with 15 fields, with a coupling between them, very specific. Then I will start losing interest in inflation. But if this model of a single field with a simple potential reproducible we see, then it's true inflation is weird. But it's producing a lot of things.
And so what do you mean by evolving again there? That I didn't find
Where-
confusing.
Point
Perturbations
point.
re-enter the Hubble
So
radius
there's
and
time
they are
difference.
evolving again.
Because the 2-point function becomes time independent when
Yeah.
it's time. So, but when enters, the time dependence gets on again.
Okay, so does the CMB also has this time dependence?
No, because the CMB
It's frozen at one.
right, the CMB is photons that copy what they have around them and they just evolve freely. But in order to predict what we see in the CMB, we need to evolve our 2-point function again from this time to this time. We need to add that evolution. But we know that there are codes, numerical codes that that do this evolution for you.
So during the reheating period, the electrons and the protons that appear inside this horizon, they are going like this, and those perturbations are coming in contact with them. Like, how is this? Like, if you have electrons and protons at this time, will they not
they are
gravitationally go into the homogeneous
Right, because
and
right.
start evolving then?
Right. I mean, here I am just drawing. I am just drawing the evolution of delta x in that.
Yeah.
But perturbations are in all scales. So and it's just I am just drawing the two-point function here, but I will have all the two-point functions there. And this two-point function really is describing a spectrum that you have over there, an arbitrary stuff. It's not only that you only have perturbations here and there. Any arbitrary field, you can do with the two-point function, and we'll have. So the perturbations are everywhere, and the electrons and protons will fall wherever they are. I also wanted to do the same computation in momentum space because that is familiar with everybody. It's in every book. So, but the way that you check that the Hankel functions become time independent is exactly this. The same. This appears to show that the Hankel functions, except with the two. For the Hankel functions, to prove that they are time independent, this is what appears. That you apply exactly the same, and they cancel exactly in the same way.
This is much more clear.
I believe this is much more clear because this is real space. This is what happens. This is what happens with correlations at different points.
So if this field is there, then are there some particles of this field?
I mean,
Also?
you can interpret. Again, we are in a current space
Like
time.
you have electromagnetic field, so you have photons, so you must be having some inflation ons, whatever. Inflatons.
But remember, we are in the vacuum state, and we are working in the Heisenberg picture. So.
But this field is still there.
The field, of
in
course.
the present time, right?
I mean, we believe that all its energy is lost here in heating in particles. So it should be now in a ground state that we cannot measure. There are theories that say maybe it's the Higgs boson with something. Maybe it's the Higgs boson, that something happens with Higgs boson that also appears at energy scales.
The idea that field gave rise to the particles that we see. During the heating, it produced particles.
It's a fundamental field, we don't know. It's just an effective field made of something else, of two fermions, or who knows? This is just an effective description. If you assume that there is something like a scalar field with something like a potential, inflation happens. This is Starobinsky potential. When you have, you have the action for gravity, which is R. And he says, okay, if you add this, then this can be translated to a scalar field and a potential. It's dual to a description of GR with a scalar field and a potential. And that really matches is the best potential, this Starobinsky potential, the one that best fits the data. So maybe it's just purely gravitational wave freedom, or something else.
Then gravity is different.
Right, then gravity is different. We don't know what it is, but I think.
But then does it completely agree in all predictions, not just pertaining to CMB fluctuations, but if gravity is different, then you should have some.
Right, but this is 10 to the minus I think minus 12 the Planck scale, the Planck energy. So we cannot feel today those changes. They are so high energy scale that for us this gravity is completely gone today. And I think this is very compelling intellectually. But when somebody presents you inflation, it's such a weird thing, a scalar field. But I see this model that this can produce the inflation. Oh, I like that.
Yeah.
Any quantum gravity theory?
Gravitational waves with two black holes or something. That energy scale is not.
No, come on. This is way much beyond what you can get. This is the Planck scale is 10 to the 19 GeV, the Planck scale. So this, we are talking square because we have to compare with the square. So the Planck scale is 10 to the 38 GeV square. Here, you are. If you take 10, we have 28. You have to compare with LHC. LHC is 1 terabyte, which is 10 to the 9, so 10 to the 18. Sorry, no. 1 terabyte, so it's 10 to the 6 gigabytes square.
Yeah.
So you are still 22 orders of magnitude far from. So you are very
No, but
far.
in gravitational ways, like in black hole, not in LHC.
Yeah, but this number is well within the constraints by astrophysical measurements.
In fact, gravity in the surface of a horizon is very weak because the larger the horizon is, the weaker is gravity. So it's extremely far from that.
And R is much below today, so R square term is much more negligible.
Okay, but because this is not a course on cosmology, it's on quantum field theory and science. This is what I wanted to say, and I think it's an extremely nice example of how useful and important is quantum field theory in quantum spacetimes today. For me, it's the nicest prediction or application that we have today, and because it's also beyond 6 we have to finish, and this is the third example. I did Hawking radiation. Is also conceptually very important. The Unruh effect and whatever you want to do in free Robinson Walker is also very very similar. And with this, I want to finish at least for this time what I wanted to say. Maybe I will give some additional lectures on more formal.
I have one more question based on a dream that I had, which was based on this course. So if you have two people falling in the black hole, so as we said that near the horizon, the what is a particle is not uniquely defined. So if me and Brajesh are falling in this, so when we are far away, I see like he's Brajesh and he see I'm Sahil. And then we go near the horizon and his frame is different and mine is different. So his notion of particles, is he still Brajesh to me? I don't know. Like, what is he? Or do I still look like
Did you drink something before going to sleep?
So what happens to a person who is falling? If the notion of particle is not
Let me
defined?
the phone. I want to finish the class here. I'll be back in a second. So that is.